Sorry about that.
That's all good. I totally get it. Totally understand. Yeah, so, alright, how you doing?
Better.
Yeah, alright, good, good. Okay, well, we were dealing with horizontal...
Horizontal asymptotes, and then I'm looking at your notes.
Exactly. Yeah, does that ring any... I mean, we never went over this, but I'm assuming your teacher did because your teacher listed it as one of the things you gotta know.
Maybe he did, but I'm writing this down because I don't remember any of this.
Okay, alright. Yeah, I was actually wondering, like, over the last, like, week or two, I was wondering, like, I'm used to, by this point, going over horizontal asymptotes with students, and it just didn't come up in any of your homework assignments, so I think, like, the big thing you do have to remember, though, Ash, is that this is an entirely different situation than the whole limits to infinity situation, you know what I mean?
Which kind of sucks.
Yeah, it's kind of annoying, exactly. Because they both obviously feature analyzing the exponents in the numerator and the denominator and comparing them to each other and all that stuff, so. But, yeah, so basically, I mean, the notes that I just sent you, that pretty much sums it up, where if the exponent up top is smaller than the exponent down below, then it's a horizontal asymptote on the x-axis. Alright.
Okay.
So it's like a dotted line that's horizontal and it passes through the origin. And then the second rule says that if the exponent up top is the same as the exponent down below, then the horizontal axis is actually at a over b.
Horizontal axis.
Or horizontal asymptote, rather. My bad. Right, it's actually at a over b. So,
And what does that mean?
so like, for example,
Oh, it means that the horizontal asymptote is the coefficients.
yeah, it's like the fraction that would be created by the coefficients.
Okay.
So just to make it very clear, Ash, like imagine you had something like 3x squared plus 1. Yeah, you could write
3x. 3. Okay, yeah.
3x squared plus 1 all over 4x squared plus 1. So imagine you had something like that. Alright.
Okay. And
So,
then it would be 3 over 4 as the horizontal
asymptote.
yeah.
Yeah, it's late. I think it's late. That's the thing. Like we're like we're like running
Well,
on
with the A.
we're running on fuse. Yeah, whatever. I totally get it. So it's like 3/4 is where the horizontal dotted line passes through. Okay, it passes through the y value of 3/4. All right.
Okay.
Do you get that?
Yeah.
And then if the third rule says that if the exponent in the numerator is bigger than the exponent in the denominator, then all you need to know for now is that there's no horizontal asymptote.
Yes.
No horizontal asymptote.
Would you say horizontal asymptote is 0, or would you just say does not exist?
It does not exist, yeah.
Okay.
Okay. Like there isn't one. Alright, there isn't a horizontal asymptote. The first rule makes it so that the horizontal asymptote is passing through the origin, therefore the equation of that horizontal asymptote is y equals 0. Alright, that's the first rule. Okay.
What is it? Wouldn't it be, if it's on the x-axis, it's x equals?
Now, remember the equation of any horizontal line is always y equals some number. And in this case, that number is 0. And here is a reminder of what it looks like.
Okay.
You know what I'm saying? So it's like y equals 0. In other words, which y value is that horizontal line passing through? Well, it's passing through the y value of 0.
Okay.
All right.
So then back to number 13, since the denominator is greater, there is a horizontal asymptote.
Mm-hmm.
And it's 1/2? Or does it take the larger one?
The exponent in the denominator is greater. Oh, yeah. I'm sorry. Which problem are we on? Number 13.
Yeah.
Yeah. So the exponent in the denominator is greater. So which rule speaks to that? It's the first one. So that means that the horizontal asymptote is on the x-axis. Okay, according to the first rule.
Don't we have to say what it equals?
Well, I mean, the equation of that horizontal asymptote is y equals 0. That's definitely true.
So it equals 0 because of the 0 exponent in the numerator?
Yeah, so if you look at like rule number 1 in those notes that I just gave you.
I understand that the denominator is greater, so then there's going to be horizontal whatever, the HA. But I don't understand where you're getting 0 from.
Yeah, so maybe I just shouldn't use the word 0. Let's just put it this way. According to rule number 1, the function presented in problem number 13 is such that the horizontal asymptote is on the x-axis. Okay.
But how do you know? It could have been on any horizontal axis, whatever, HA.
Well, because according to rule number 1, in the notes that I gave you, when the exponent in the denominator is greater than the exponent that's in the numerator, whenever that occurs, that means that the horizontal asymptote is on the x-axis.
Okay, so it can only be the x-axis.
Exactly. Okay. Yeah, so anytime the exponent in the denominator is bigger than the exponent in the numerator, then the horizontal asymptote is only on the x-axis.
So the only time for change is if the exponents are equal to each other.
Yeah, totally.
Okay.
Exactly. Yeah, very good. Cool.
Can we do another one?
Yeah, I think we should do another one like that. Ooh, this is a good one. I like this one. Alright, so please give me the horizontal and vertical asymptotes of this one.
Okay. So for your horizontal, they are the same, so it would just be 3.
Totally.
And your vertical, you would have to do x plus 2 times x squared minus 2x plus 4. Right? And then set those equal to 0.
You know what? It's not bad, but it's actually a little easier than that in that basically you want to put the denominator and just set it equal to 0, right? And then you're going to want to solve for x. Well, let's do that. So you have x cubed plus 8 equals 0. And you know what we're going to do right now? Instead of like factoring that thing, let's just subtract 8 from both sides like right now. And what do you end up with x cubed equals negative 8. And take the cube root of both sides.
You get 2, but what do you do with the negative?
Yeah, actually it would end up becoming x equals negative 2 because the cube root of negative 8 is negative 2. So negative 2 times negative 2 times negative 2 is 8, and negative 8. All right. So basically, what that tells us is that without a shadow of a doubt, there is a vertical asymptote on negative 2. All right. One more like that, just to let it really sink in. Okay. Please give me horizontal and vertical asymptotes for that.
The horizontal, the denominator is larger, so it's y equals 0 when it's on aka x-axis.
Totally. Oh my god. Freaking awesome. Really good. That was like, bam, bam, bam.
And then your other one is plus minus 8.
Exactly. Good job. Think you got it.
I think so.
Mm-hmm. All right, cool. So that's that. And then let's see.
Going back to the graph,
Mm-hmm.
the only time that the filled in dot is used is when you're talking about you have f of x, right?
Mm-hmm.
Okay.
Yeah. When it's like f of x, when it's not a limit question, right? So if it's a function question rather than a limit question, so they're like, you know, like what is the limit of f of x as x approaches 4? Well, the limit of that graph as x approaches 4 is 5. Okay. But if they ask you, what is f of 4?
It would be 2.
That's 2.
Okay.
All right. Okay. So what's confusing about your notes is I think that as you were taking the notes, you just made like little mistakes. Like for example, it should be 3 minus x in those parentheses. Okay. You have 3 minus 1 in those absolute value symbols rather. All right. So that should be 3 minus x over x minus 3. Okay. Now, this is a different scenario where we're now investigating the limit as x approaches 3 from the right.
Mm-hmm.
All
So
right.
you get 3.1.
Yeah, so you'd replace x with 3.1. And therefore, it's 3 minus 3.1 in the absolute value symbol. Since that plunges you into a negative,
Mm-hmm.
what you want to do is anytime you get plunged into a negative value, yeah, just like the last problem, you're going to drop the absolute value symbols again,
Mm-hmm.
but now you're going to make the entire numerator negative. Alright, so that's the trick of the trade. So it ends up becoming negative quantity 3 minus x as opposed to just 3 minus x. Alright. If your test value plunges you into the negatives with within the absolute value symbols, well sure, you're going to drop the absolute values of symbols again, but now you're going to stick a negative in front of that whole quantity. So when you do that, you end up with x minus 3 over x minus 3, and that ends up just becoming 1 as the answer. Alright?
-6.
Yeah, negative 6.
5, which gives you -1. Yeah.
Well, negative 6, we're replacing x with a -6. So it's really a -6 minus 5. Now that -6 is just a +6.
Okay.
So that ends up just becoming 6 minus 5, which is 1. And so we have a positive number inside the absolute value symbols right now.
Yeah.
When that happens, you drop the absolute value symbols and you keep the exact same scenario.
Okay, so then you would have negative x plus 5. Oh, and then you would you take out the negative, and then you'd get x plus 5, cancel it out, and then you're left with -1.
Exactly. Yeah.
Okay, that makes sense.
You see that? But
Yeah.
we see how we're like abiding by the exact same rules that we had before, right? So, you know, if you end up with a positive number on the inside of the absolute value symbols, you drop the absolute value symbols and you keep the problem looking exactly the same. Okay. Number 4. Okay. Negative infinity. Okay, well that's yeah, so that's already right there negative. You know, I mean, you don't even have to do any test values at all. That's just straight up shoving a negative number into the absolute value symbol, right? So what does that mean? You drop the absolute value symbols and you turn whatever was inside those absolute value symbols into a negative.
But if it's already negative, does it make it positive? No.
Well, I just want you to pay attention to that one move between where it says op of and with the arrow. Just want you to pay attention to that move only. You understand?
But I feel like you just get rid of the opposite value sign, and you just take the negative from the infinity and put it in.
I mean, you could kind of think of it that way, but I want to get you thinking in terms of the general rules that we're using for all of these problems. And the general rule that we're using for all these problems is if you put a number into the absolute value symbols that causes what's inside of the absolute value symbols to be negative, then in the next move after that, you're going to drop the absolute value symbols and you're going to negativize whatever was inside those absolute values.
Okay.
Okay? So we're negativizing x in that one moment.
Yeah.
Which is exactly what they did. It's 5 minus 7 times negative x. Right? And then you just do algebra from there. Right? It's a negative, so it becomes a positive, blah, 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 blah. All right. You got that?
Yeah.
Would you like a practice problem?
Sure.
All right.
Okay, thanks.
No problem.
Instead of, so you drop the absolute value signs, and then you have a negative, and then x minus 10 in parentheses, and then x minus 10, and then those cancel out, and you just get a -1 as your answer.
Exactly so.